Hello everyone, I'm Zhiyong. I'm from University of Washington, and I'm from the Smart Transportation Application and Research Lab. As you can see, this is a beautiful scenery in Seattle. Our research topic is deep stack bidirectional and unidirectional LSTM recurrent neural network for network-wide traffic speed prediction. So I will first introduce our background and then methodology, data description, and then I will let you know the results and the comparison and then conclusion. So actually, the short-term traffic forecasting has always been the the major component in the ITS applications. As you can see, this picture, this is a big data traffic transportation big data platform developed in our lab. And we are hosting different data sources, also the real-time data and the historical data. And the traffic prediction for this whole traffic network is very important for our system. So we are aiming to solve this problem, but according to the existing literature, we can find that the traffic prediction model can be divided into two categories. The first one is like the classical statistical model, like the ARIMA, and the second one is the computational intelligence methods. Actually, it is just the artificial intelligence methods. In recent years, there's some changes emerging, like the volume of the transportation data has been increased, and the traffic condition becomes more complex, and also the deep learning methods. The deep learning developed very fast in the recent years. So then we are focusing on the deep learning method. Actually, neural network methods has been adopted by the traffic prediction problem early in around 2000, the year of 2000. They tried the feed-forward neural network, fuzzy network, and the recurrent neural network. But in recent years, most studies come to focusing on the LSTM. They try the LSTM to do the speed prediction, travel time prediction, and traffic flow prediction. Actually, I think this is because the popularity of the deep learning, and LSTM is a fundamental building block for the time theory or the speech analysis models. And then in this year, there's some other works. They combine the convolutional neural network and the LSTM neural network. Actually, they just convert the traffic network into image and then use CNN to learn the features. But actually, the potential of the deep learning models is far from be fully exploited in terms of the spatial scale of the prediction area. The prediction area has not been expanded to the network-wide in most studies. Also, the depth of the architecture is very shallow. In some studies, they only use one layer of the LSTM. And also, for the long-term feed-forward dependency of the traffic data, are mainly be inputted into the model in the chronologically into the model. But for this cases, like in this example, if we want to predict the status of in the time t, we will use the historical data and process the data in the forward direction. But how is the performance if we want to measure the status of the traffic in another direction? No work has been done to do this, and also for the prediction power, it is not good enough in many works. So why we need to consider the backward dependency of the traffic time series data? I think there's several reasons. The first one is if we want to use the time series data, actually the traffic pattern has strongly periodicity, and also the network wide traffic pattern needs to consider the upstream and downstream. But for the complex traffic network, actually the upstream and downstream are relative. Like if you are driving on the road, you make 4 consecutive right turn, you will be on the same corridor, right? So considering this, the bidirectional LSTM is a good option, which considers both the forward and backward dependency. So then I will state our problem. Like we want to measure the network-wide traffic speed, and if we want to predict speed at one location, we will use the time sequence. But if we want to measure the traffic network with like multiple locations, the input of the model should be a matrix, and you can see in this matrix the horizontal axis shows the temporal information, and the vertical axis shows the spatial information. And this picture shows the one of the data source in our system, and the blue icon shows on this map is the sensor location of the freeway system in Seattle area. So then I will briefly introduce several building blocks of our framework. The first one is RNN. Actually, RNN has a chain structure, and it has been shown that it has great power in the time series data process and the sequence prediction. Actually, the most important part of the RNN is the hidden layer. In each direction, the output of the hidden layer will be feedback into the hidden layer in the next training iteration. So actually, in the LSTM, in the RNN hidden layer, there's only 2 weight metrics. So then is the LSTM. The long short-term memory neural network, it is capable for learning the long-term dependency. So what's the long-term dependency? Because in the RNN, there's normally has a problem. It's called the gradient diminish or the gradient blowing up. Like when the RNN's iteration is the length of the iteration is very long, the gradient may be diminished. So in the LSTM structure, they have 3 gates, and these gates can solve this problem. In the literature review, they found that the forget gate is very important for this LSTM cell. And it has 3 gates. This is the forget gate, this is the input gate, and this is the output gate. And the 2 C's are the input and output of the cell, and H is the hidden state, and also HT is the final output of this model, of this layer actually. And then it's the bidirectional LSTM. This idea comes from the bidirectional RNN. Actually, it has been developed many years ago, but it has usually adopted for the speech recognition and the sentence translation problems. The bidirectional LSTM, it has two LSTM layer. One is in the forward direction, and the other is backward direction. And the outputs of the 2 layers will be combined by the sigma function. Actually, the sigma function could be summarize or average or multiplication or others. In our work, we choose the average method. So this is the framework of our proposed method. We call it a stacked bidirectional and unidirectional LSTM neural network. Actually, we first put the network-wide speed as the input, and then the first layer should be the bidirectional LSTM. As we expected, there should be several middle layers of bidirectional LSTM, and then the last layer is the LSTM layer. Actually, according to our test and result, this framework without the middle layers, without the middle bidirectional layers, works best. So I will then describe our data. This data comes from the induced loop detector deployed on the highway system. It can detect the volume and the speed of the traffic, and we extracted more than 300 sensor locations from both directions on the freeways on these 4 highways, and we used the 5-minute interval data in the year of 2015. Actually, we also use 10 time lags to be used as the input of our model. Actually, 10 time lags means 50 minutes, and and the spatial dimension is 323. Firstly, we compare our model with some classical method. We didn't compare our model with the ARIMA method and the Kalman filter because in several literature they said these 2 methods cannot compete with neural network. So we compare with SVM, random forest, feed-forward neural network, and a gated recurrent neural network. I think also we measure our model using the mean absolute error and the mean absolute percentage error. All these 2 metrics shows that our model works best, and but also you can see the random forest and the feed-forward network also works very good. But still, I think after more training, we found that our SBU LSTM works better than the other 2. We also compare our model with other LSTM-based model. As you can see, we compare with the pure LSTM, and the second one is the LSTM with a layer which is the fully connected layer, and the third one is the LSTM neural network, and we also consider the temporal information like the hour of day and the day of a week. The third compared method is the pure bidirectional LSTM, and then in the horizontal axis you can see the n shows the number of the LSTM and bidirectional LSTM layers. We found that actually when there's no middle layers for our model, it works best, and the result shows at the left bottom. So then we also compare the number of time lags of the model. When actually this box plot shows the MAE of the comparison result when we training our model. When the input has 6 time steps, the performance is not satisfactory for us. But when the number of the time lags increase, the performance became pretty similar, and I think this can be interpreted as the pattern in our data. I think if the time is less than 30 minutes, there may be some problem to fully obtain the traffic pattern. And then we compare the spatial dimension of the weight matrix in our model. Actually, this weight matrix means the weights in the LSTM layer and also the bidirectional LSTM layer. We found that whatever we change the weight dimension of the matrix, the performance keeps in the same level. So then we to show our performance, we plot the heat map of the ground truth and predicted value of the whole network. We take 1 day for example. As you can see, the different color, the color shows the speed in different sensor locations. The MAE and MAP of each day of the week are nearly the same. So that means our model works for different traffic pattern, and also the average MAE is 2.4. That means the average error of the prediction is of each sensor location is 2.4 miles per hour. The result of the results of this model is pretty similar. The spatial and temporal pattern are, I think they are obtained during the training process. So in these slides, it shows several examples of the simultaneously predicted values on different sensors. Actually, we extracted data from 4 freeways. So we pick up 4 different traffic patterns from these corridors. And as you can see, these are the predicted results at the same time for this 4 sensor location. The train of the predicted line is very similar to the true speed. And then we also visualize our result in the true map. You can see the different color shows the speed in different area. The actual congestion map and the predict congestion map are extremely same. Yeah, actually, it mainly shows the interaction area of the 4 corridors. I think that should be more interpretive. So in this work, we proposed the stacked bidirectional and unidirectional LSTM for the network-wide traffic speed prediction. Actually, we expanded the traffic predict area into the whole network, and we adopt the deep stacked architecture, and we analyze the influence of the number of layers. Also, the forward and backward dependency has been considered in our work. Actually, as we tested, the 2 layers of SBU LSTM, it works best. So then there's another question. Does this method consider the spatial influence? As I just showed you, we measure the 4 corridors. Actually, we didn't adopt any structure or say mechanism to arrange the sensor locations in our training data. We just convert this data into a vector. I think the spatial influence has been considered in this model, but because they are captured by the weight matrix of the LSTM layers, but actually it is hard to interpret it. So in the future work, I think we will consider more complex traffic network, and also we will try to adjust the LSTM neural network to interpret the spatial influence of the sensor location between each other. And this is several of the reference. And thank you for your attention.